Hello, everyone. My name is Anya Skredo. I will be moderating this session, and this is the session that I'm really excited about, as this will be all about data visualization and how people interact with charts. So let me invite to the stage Emily Robinson, PhD candidate in statistics at the University of Nebraska-Lincoln, with her presentation, You Draw It, implementing human interaction in R Shiny with R2d3. Emily, are you ready?
Yes, I think, can
Great.
you hear
So
me all right?
yeah,
Awesome.
the stage is yours.
Awesome. All right, yeah, thank you, Anna, and thank you everyone for coming to my talk at whatever time it happens to be where you're joining from. So I'm going to be sharing some of my work using R2d3 and Shiny to test statistical graphics. So during my talk, I'm going to first provide a brief background on graphical testing and how it relates to detecting trends and patterns in data. Then I'm going to talk about the development process behind the scenes, and you'll get a chance to actually test out your drawing skills. And then finally, I'm going to share some results from the validation study and plans for future work that I have. So we all use statistical graphics, but how do we know that those graphics that we're using are communicating properly? So through experimentation, graphical testing methods allow researchers to conduct studies geared at understanding human ability to conduct tasks that are related to the perception of statistical graphs and charts. So some of these tasks might involve differentiation, prediction, estimation, and even extrapolation. So a lot of efforts in the field of statistical graphics have developed graphical testing tools and methods, and all of these different types of tests require different levels of use and manipulation of that data being presented in the chart. And so with the advancement of graphing software, we now have the tools necessary to develop new methods of testing these graphics. So one such aspect of interest is the ability to identify and detect trends. So our visual system is naturally built to look for structure and identify patterns. So for instance, points going down from left to right indicates a negative correlation between the X and Y variables. So initial studies in the 20th century explored the use of fitting lines by eye through a set of points using physical manipulation methods, such as maneuvering a string, black thread, or ruler until that fit is suitable. And then they'd draw that line through the set of points. And then recently, a study in 2021 conducted a pretty comprehensive set of studies investigating human ability to detect trends in graphical representations from more of a psychophysical approach. So the big goal here is how can we compare our intuitive visual sense of patterns to those determined by statistical methods? So in 2015, the New York Times introduced an interactive feature called You Draw It, where readers inputted their own assumptions about various metrics, and then they could compare how these assumptions relate to reality. And the New York Times team utilizes what's called data-driven documents, D3, so we'll talk more about this on the next slides. But this allows readers to predict these metrics through the use of drawing a line on their computer screen with their mouse. And so the goal of my research is to implement this kind of You Draw It feature as adapted from the New York Times feature as a way to measure patterns that we see in data. And so in the rest of the presentation, I'm going to provide kind of a high-level overview of the technical details of that software development, which utilizes interactive graphics in R. And then I'm going to share results from a study which validates this You Draw It as a method for graphical testing, and recommend an appropriate data analysis method to that participant data as well. So a little bit about data-driven documents, or D3. This is a JavaScript-based graphing framework that facilitates user interaction. And so if you're familiar with ggplot, gplot is to R as D3 is to JavaScript. And so this is used by major news and research organizations such as the New York Times, 538, Washington Post, and Pew Research Center to create and customize graphics. And so a big benefit is that with D3, it's a lot easier to implement user interaction and animation into the graphic. So one of the main challenges of working with D3 is the environment that is necessary to display the graphics and images. So the R2d3 package in R actually provides a really efficient integration of the D3 visuals in R by displaying them in familiar formats such as R Markdown with the HTML outputs or Shiny applications, which I'll talk about here today. And so this is a really amazing way to implement that interaction. And so the big thing here is that R2d3 makes it really easy to do kind of your data processing in R, since we're all probably very familiar with that. And then you can apply that specific D3 JavaScript source code in order to visualize that data. And so here the example R code illustrates the structure of the R2d3 function, which includes specification of a data frame in R. This needs to be converted to a JSON file, and then the D3 source code file that is kind of living off on its own, and then the D3 version that accompanies that source code. And so this R2d3 function will then render the plot using that source code that you specified. So when I first started working on this, I was really comfortable working with R and Shiny. However, I had almost no experience working with JavaScript. So I wanted to share some resources that I found really useful in learning to create graphics using D3. So one thing to know is that D3 uses SVGs, or scalable vector graphics. So this preserves the shapes rather than the pixels. And then it follows kind of a layered element framework. And then I also highly recommend Amelia Wattenberg's Full Stack D3 and Data Visualization book. In this, she doesn't use R HTML formats as her environment, but the examples and the D3 source code can easily be implemented in any of the formats that you might be familiar with. So here you see an example of the developed UDrawIt interactive plots. In graphical testing, participants are prompted to use their mouse to fill in the trend in the yellow box region. And so this yellow box region then moves along as the participant draws their trend line until that yellow region disappears. And so I believe in the chat, there was going to be a link to this Shiny app here. And so you can use this, use your mouse to test out your drawing skills at that link. And then also feel free to take a look at the working pieces kind of behind the scenes with the Shiny showcase display mode. And we'll talk a little more about those on the next slide as well. But if you kind of want to go to that link there, it might not. I wonder if it's not working for you. I'm guessing there's a high magnitude of people, and just give it a second and try again in a few minutes. But I'm guessing it's not built to handle such high magnitude all at once. So as you're kind of trying some of that out, okay, I'll put the link in the chat again. All right, so if you kind of want to keep trying that as time goes on, it's just kind of for you to test out. So if you kind of got in early, you probably were able to test it out. So I kind of wanted to provide kind of a code sketch of what was going on. Like I said, the display mode with the showcase is there so that you can kind of look through the server and the UI and the D3 source code a little bit as well. But how this kind of is working behind the scenes is that we conduct all data simulation and processes in R and then output two data sets. This involves a point data set and a line data set. So we have to pass two data sets into the D3 JavaScript code. And so these both contain the X and Y coordinates corresponding to either a simulated point or the fitted value predicted by a statistical model, respectively. And so the R2d3 package then converts that data set in R to a JSON, which can then be interpreted by that D3 JavaScript code. And so in the D3 JavaScript code, we define functions to draw that initial plot and set up drawable points for the user's drawn line. And then drag events in the D3 JavaScript are utilized to observe and react to that user input. And then we also use Shiny messages to communicate kind of that user interaction between the D3 code and the R Shiny environment. And then this plot is rendered and updated on user interaction in the R Shiny application with the render D3 and the D3 output functions. And then there's also an option within that R2d3 function for you to specify different parameters for aesthetic design choices. So you pass kind of a list of options, and the R2d3 passes those to the JavaScript code. And so for instance, if you want to specify kind of a buffer space to allow for the X and Y axis to avoid users anchoring their lines to the axis limits, we have that built in there. And so I'm going to now talk a little bit about the validation study that we used for this tool. So we conducted a study in order to validate UDrawIt as a method for graphical testing, and we compared it to a less technological method utilized in this 1981 paper. So in this 1981 study, participants were asked to fit lines by eye to 4 sets of points using an 8.5 by 11 inch transparency sheet with a straight line etched across the middle, and they kind of moved that around until they were happy with the fit. So their results showed that students tended to fit the slope of that first principal component as opposed to the slope of the ordinary least squares regression. And so in our study, we wanted to replicate this so that we could use it as a method for validation, but participants were asked to draw a line through a set of points with that UDrawIt method. And so we simulated data meant to reflect those 4 data sets from the 1981 study. So we had the same 4 kind of names of those data sets. And so this experiment was conducted and distributed through an R Shiny application in which participants kind of clicked through the different UDrawIt task plots. So then we were interested in comparing participant drawn lines to 2 regression lines determined by the ordinary least squares regression and the regression based on that principal axis or that slope of that first principal component. So this figure illustrates the difference between the ordinary least squares regression line, which minimizes that vertical distance of the points from the line, and a regression line based on the principal axis, which minimizes that Euclidean distance or those points orthogonal from that line, which captures the variability in both the horizontal and vertical direction. And so then from our study, as participants are drawing, we collect that data on the participant drawn values. And so we can get out of that the participant drawn values, as well as the fitted ordinary least squares regression and the fitted values from the regression based on that principal axis. And so each participant for each plot had a unique independent set of data generated. And so each one's going to kind of have a slightly different one, while the underlying parameters are the same for each of the kind of parameter choices. And so since they're all different, what we're mainly interested in is actually that deviation of the participant drawn line from the fitted line. And so while it seems really counterintuitive, our residual between the drawn line and the fitted lines actually becomes your response when you're kind of evaluating this data. And so in order to analyze this data, we used both linear mixed models and generalized additive mixed models to evaluate those vertical residuals and compare the drawn lines to those fitted trends. And so here we can kind of see results from our study. And so they were consistent with those found in the previous study, that when shown points following a linear trend, participants tended to fit the slope of the first principal component over the slope of the least squares regression line. And so this trend was most prominent when shown data simulated with larger variances. So parameter choices F and N had a much larger variance than S and V. And so we can see that participants the residuals are following a lot more of that horizontal y equals 0 line, which means that they're following that line a lot more carefully. And so if you got the chance to test out the drawing, you maybe saw a light blue line pop up at the end, and you may have kind of underestimated early on and then overestimated later. That light blue line that popped up was the ordinary least squares regression line. In the study, participants weren't shown the true line after they drew their plot, but it's kind of fun for testing it out to kind of see where that's at. And so one of the benefits of using a GAM then is that this allows for estimation of the smoothing splines and allowing for flexibility of that trend. And so maybe here participants weren't restricted to fitting a straight line. And so we can kind of use that. And so this lays the foundation for the use of GAMs as an analysis method of the collected data, so that maybe you can look at trends that maybe aren't necessarily straight lines, that you're not restricted to that. So the big idea here is that this study reinforces that difference between the intuitive visual fitting model fitting and that statistical model fitting, which provides us information about that human perception as it relates to the use of statistical graphics. And so while I presented some technical details here, I do intend to create an R package designed for easy implementation of this UDrawIt task plots in order to make this tool more accessible to other researchers. Still kind of trying to think through some of the working pieces of that. Right now, it's very customized to be a one-to-one type of plot, but kind of envision hopefully creating some sort of add-on to Shiny that could be implemented there, so that you're not having to deal with the behind the scenes all the time. And then also further investigation with this is necessary in order to implement this method with maybe real data. I envision it being useful for facilitating scientific communication, and also being able to evaluate the ability to make future predictions and look at forecasting biases. For some of my dissertation work, I'm looking at people's ability to make predictions of exponentially increasing data displayed on both maybe the linear and log scale. And so that's where kind of the GAM comes in handy in that analysis method. And then we do have a publication under review right now for the validation study of this. And so I want to give a big shout out to my advisors at UNL, Dr. Susan Vanderplas and Dr. Reka Howard, for guiding me through this research and kind of brainstorming with me as we go. And thank you everyone for coming to listen today.
Thanks a lot. That was a great presentation. We have some questions, so I will just read them out. So first, about assumptions. So what were the assumptions, primary assumptions to your models?
Yeah, so I assume we're talking about the models used to analyze the participant feedback data. So with the linear mixed model, I guess our study was implemented as kind of a randomized complete block design, where each participant saw all four of the different parameters in kind of a random order. A previous study had done a Latin square design, and they found that order didn't really matter. And so we weren't sure, like, if the practice effect would have anything. So we just did a random order, but we accounted for that participant variation into that model. And then the generalized additive mixed model, we did the same, where we accounted for that participant variation. We also included a participant variation for that spline effect part as well. In that, we don't have any autocorrelation accounted for, and so that's one thing that I had wondered about. So I think we're making an assumption on that part of it.
Mm-hmm. Thank you. And what was your biggest difficulty, your biggest struggle during that study?
Honestly, I think it was the JavaScript code. That it was really fun, but I'd get really frustrated at some points. And so it's something that I kind of want to keep working on my skills at. But once I got it, like, you can do some really cool things. It's just having the time to sit down and really learn that inside out.
Mm-hmm. Great. Yeah, I'm also learning currently JavaScript, so I can understand your struggle. And about that learning. So would you recommend learning JavaScript and D3 to all people that want to make some cool visualizations, or just for some specific group of people? What's your opinion here?
I think if you have really solid coding skills in ggplot and understanding of how kind of that maybe grammar of graphics or layered graphics works, that it kind of builds off of itself, you can make that jump. I mean, it can still be frustrating, but you can make that jump pretty easily. And I would recommend if you want to have user interaction, it just goes a lot smoother than some of the other maybe easier to implement user interactions. And then it's very reproducible with that code script. And so I recommend it, but also I don't know that it would be the first one I would jump into if you don't have kind of a base of another language.
Yeah, sure. Thank you. Let me check the questions. Did you somehow made metric invariant to shaking hand while drawing with mouse? Interesting one.
Can you repeat that one more time?
Did you somehow made metric invariant to shaking hand while drawing with mouse?
Yeah, so that was one of our concerns of if it would even be a valid way to test it. And so that's kind of why we did the study that we did with that eye-fitting straight lines. And so we did talk about, like, we didn't end up doing it, but we talked about maybe the need to fit like a lowest smoother over the participant draw line to say, okay, here's kind of the trend that they were trying to fit. And so making an assumption there, we didn't end up doing that because we saw the results that we wanted without having to do that. But that was one of our concerns. And I guess I don't know that there's a way that we necessarily accounted for it other than kind of looking at those two different ways of possibly analyzing the data.
Mm-hmm. Sure. And did you ever thought about testing whether people can tell from a time series graph whether a new observation is significantly different than trend or expectation?
Yeah, so I know a lot of the work that I've been working on, I've been thinking about kind of taking and implementing into a time series aspect. And so there again, you can look at differentiation of some of identifying those change point detections. We also talked about in some of these studies, providing an outlier and seeing if that affects people's slope or adjustment of the line or trend of whatever they're looking. There are a lot of studies out there that humans can actually extrapolate pretty well on like sine curves and things. And so that would maybe extend a time series where, they aren't showing points throughout and then like you ask them to make a prediction later on and they're able to kind of visually see where they think that trend would go and be pretty accurate in their estimates. And so there are a lot of applications there that I think that this would be really useful in.
Mm-hmm. Thank you. Another question, additional to the mouse question, were lines drawn with the mouse or on tablet with finger pen, and if that would make any difference? What do you think?
So using kind of a pen or finger, I wondered, I do have a version of this that I had like a QR code that you could go onto like your phone and scan and test it out. I think at least, granted, I've been drawing it a million times, so I've probably gotten good practice with it. But I do think that that might be helpful. I know that we conducted a much larger study than the pilot study that I presented here. And in that we asked participants if they used a mouse or like if they had a mouse on hand or if they used their trackpad. And so we just got that data back last week. So I haven't done any analysis of that yet, but I think we're going to try to analyze and see if there's any effect there just to see, could this improve it? And I guess going forward, something might be to have people do it on a tablet with a pen versus with a mouse and kind of compare that as well. But that would be very interesting.
Or maybe they can first have some like test, draws, and then like if they have practice, then actually, the errors are with the trends.
Yes. Yeah, and that's a good point that in our study, we actually did have two practice test plots before they did their actual plots. And so this kind of walked them through directions of, make sure you're grabbing the edge of the graph. You can go back over your line, you can reset it. And so we did a little bit of training in just kind of what it takes to do this well, I guess.
Okay, great. One more question. Is there going to be an official winner of You Draw It competition? So the person probably who has the smallest errors.
Unfortunately, I did not collect your data from that app through RS Connect. We couldn't connect it to a database, so I will not know who had the best drawing, but nice job.
Yeah, that could be good, motivation so that people really pay attention what they are drawing. Okay, I'm checking the questions. I don't see any more questions. Is there anything you would like to say at the end?
No, just thank you for having me and being interested in some of my work. It's fun to kind of hear ideas too, and gives me thoughts on how to proceed with some of this.
Thanks a lot. It was great to have this session with you, and hope to see you again
Awesome.
on the next Shiny conference. Thank you.
Yes, thank you for having me.